Okay, I hope I'm audible to all my students who are attending this particular lecture for the Advanced Mathematical Methods for Economics course. In this particular lecture, I'm going to start with the discussion of the 2024 question paper, which has come up at Delhi University for the Advanced Mathematical Methods for Economics course. This course is offered to all students who are in semester 3 pursuing BA Honors Economics from University of Delhi. Okay, so in this particular lecture, I'm going to start with the discussion of this particular question paper. Okay, I hope students can properly see the question paper on your screens. I'm going to start with the discussion of the first question in this particular lecture. Okay, so let's quickly start with the discussion of this particular past year paper. So let's look at question number 1. Maximize profits, where we are given the profit function as a function of the outputs x and y. X and y denote the outputs of good x and good y respectively, subject to the production constraint x plus y less than equal to 36. Okay, so we need to, it's a simple profit maximization problem and it's a constraint optimization problem because we need to maximize profits subject to a given constraint. Now students can recall my lectures on constraint optimization, which I have covered in my complete course for Advanced Mathematical Methods for Economics course. Okay, so let me quickly come to the whiteboard to solve this particular question. I am just writing the main heading for completeness. This is Delhi University Exam 2024. Name of the course is Advanced Mathematical Methods for Economics. I can just write MME, and we also sometimes call it as the MME-3 course. Remember, Economics Honors currently has 3 maths courses. One is Introductory Mathematical Methods for Economics offered in semester 1. Then we have Intermediate MME, also called MME-2 in semester 2. And this one is Advanced MME, which is also called MME-3, offered in semester 3 currently. Okay, recommended for all Economics Honors students. However, if you have undergraduate economics, be it in any other university, then this lecture can still be helpful to you. Okay, so let's look at the first question. Objective is to maximize profits, which is 64x minus 2x square plus 96y minus 4y square minus 13. Okay, subject to the constraint x plus y less than or equal to 36. So it's a simple constraint optimization problem. To solve these problems, we first define the Lagrange. So we define the Lagrangian. We define the Lagrangian function for the above problem as, we define the Lagrangian function for the above problem as, the Lagrange is 64x minus 2x square plus 96y minus 4y square minus 13 plus lambda times 36 minus x minus y. Remember from my lectures on constraint optimization, the Lagrange is always the objective function plus the Lagrange multiplier lambda times the constraint, the right hand side of the constraint minus the left hand side of the constraint. This is how we define the Lagrange. And now we need to maximize the Lagrange and we need to choose x, y and lambda. So my choice variables are x, y and lambda. We need to choose x, y and lambda to maximize the Lagrange. We have the following conditions. First order conditions, del L by del x equal to 0. If I partially differentiate the Lagrange function with respect to x, I get 64 minus 4x plus lambda times minus 1 equal to 0. Remember from my intermediate mathematical methods for economics course, when you are differentiating partially with respect to x, you treat y as a constant. And when you differentiate partially with respect to y, you treat x as a constant. Okay, so it's 64 minus 4x plus lambda times minus 1 equal to 0. So I get 64 minus 4x minus lambda equal to 0. Equation number 1. Then I have del L by del Y equal to 0. If I differentiate the Lagrange with respect to Y, I get 96 minus 8Y plus lambda times minus 1 is equal to 0. So I get 96 minus 8Y minus lambda equal to 0. This is equation number 2. Okay. And then we have the complementary slackness condition. Okay. So my complementary slackness, this was first condition del L by del X, del L by del Y. Then I have the complementary slackness. The complementary slackness condition is that lambda times 36 minus X minus Y, either this should be equal to 0 or lambda is greater than equal to 0 with lambda exactly equal to 0 if x plus y is strictly less than 36. Okay, students can find this in my lectures on constraint optimization where I've looked at the Kuhn-Tucker conditions and the complementary slackness. Okay, the last condition pertains to lambda times 36 minus x minus y equal to 0 or the possibility of lambda greater than equal to 0 with lambda exactly 0 if x plus y is less than 36. Okay, this is my third condition. So now I'm erasing the initial portion off because we know the question we are doing now. So I'm erasing the initial portion off. I'm writing the conditions again on the top. The first condition we have was 64 minus 4x minus lambda equal to 0. The second condition we got was, this was the first condition. The second condition is 96 minus 8y minus lambda equal to 0. And the third condition is the complementary slackness condition, which is lambda times 36 minus x minus y is equal to 0 or lambda greater than equal to 0 with lambda exactly 0 if x plus y is less than 36. Now let's analyze the third condition because the third condition further has subcases. So I am erasing all this off now. I am erasing all this off and analyzing the last condition. So case 3A. Suppose lambda is strictly positive. Now if lambda is strictly positive, it means that x plus y is exactly equal to 36. Remember guys, if lambda is 0, x plus y is less than 36. But if lambda is strictly positive, for this condition to satisfy, if lambda is strictly positive, it means x plus y has to be equal to 36, right? I can write it more clearly. If lambda is positive, let me write it clearly. If lambda is positive, then for equation 3 to satisfy, 36 minus x minus y should be 0. Because if lambda is strictly positive, 36 minus x minus y should be 0, which implies x plus y is equal to 36. X plus y is equal to 36. Okay, now let's solve for, now from equations 1 and 2. From this equation, from equation 1, I can write 64 minus 4x is equal to lambda. From equation 2, I can write 96 minus 8y is equal to lambda. So from equations 1 and 2, I get 64 minus 4x is exactly equal to 96 minus 8y because both of them are equal to lambda. So what do I get? I get 4x minus 8y is equal to 64 minus 96. If I solve, how much is 64 minus 96? It comes out as minus 32. Okay, I am just rearranging the terms. I took minus 4x to this side, so I got 4x minus 8y. I took 96 to this side, so I got 64 minus 96, which is minus 32. And this further boils down to, if I divide by 4 on both sides, 4x minus 2y is equal to minus 8. This is what I get when I divide by 4. Dividing the above equation by 4. Dividing the above equation by 4. So now let's call this as star and let's call this as star dash. Now let's solve for star and star dash. So x plus y is 36 from equation star. I don't need to write it, students know it. X plus y is 36, and then from this equation, x minus 2y is minus 8. Let's solve for x and y. If I subtract them, this is star and star dash. Equation star minus equation star dash gives me what? When I subtract them, x cancels. I get y minus of minus 2y is equal to 36 minus of minus 8, which gives me 3y is equal to 44. Y is equal to 44 by 3. What will x be? Put this in equation star. Putting y equal to 44 by 3 in equation star, which is this equation, what do I get? What will x be? X will be 36 minus y, which is 36 minus 44 over 3, which will come out as how much? Let's quickly calculate that. So 36 times 3 is 108. When I take the LCM, this is 44. 108 minus 44 is 64 by 3. So x comes out as 64 by 3. Now when x is 64 by 3, y is 44 by 3, can we find lambda? So from equation 1, what will lambda be? If I erase this particular portion off, I'm erasing this off now. And I can write putting x equal to 64 by 3 and y equal to 44 by 3 in equation star or in equation 1. On the top, students can see equation 1. Let me put these values in equation 1. So my lambda will be 64 minus 4x. I don't need y first of all. I just only need to put in the value of x. What is x? 64 by 3. So lambda will come out as, I take 3 as the LCM. 64 times 3 is how much? Comes out as 192. Minus 4 into 64 is how much? Comes out as 256. And 192 minus 256 is minus 64 by 3, which is negative. But lambda can't be negative. We started with saying that lambda is positive. That means this case is rejected. This case is rejected because the moment I start with this case and when I solve, I get x as 64 by 3, y as 44 by 3. When I plug them back in equation number 1, when I plug them back in this equation, I get lambda as a negative value, but lambda can't be negative. Lambda has to be positive. That means we cannot do case 3a. That means let's look at case 3b. That means lambda is equal to 0. So if I erase all this off, we now look at the next case, case 3b. Lambda is equal to 0 and x plus y is less than 36. Now, if lambda is 0, then from equation 1, 64 minus 4x is equal to lambda, which implies 64 minus 4x is equal to lambda is 0. So 64 is equal to 4x, which implies x is how much? 64 by 4, which is 16. And from equation number 2, 96 minus 8y is equal to lambda, but lambda is 0, right? So 96 minus 8y is 0. So 96 is equal to 8y. So y is how much? 96 by 8, which comes out as how much? If I work out 96 by 8, it comes out as 12. And is x plus y less than 36? Let's do that. X plus y will be 16 plus 12, which is 28, which is less than 36. So it is satisfying this constraint also. That means the answer for this question is x star is 16, y star is 12, lambda star is 0. This is the answer for this particular question. Okay, so hoping students have understood this. All we had to do was we had to define the Lagrange, use the complementary slackness condition, check out the sub cases. Case 3a was not satisfying, case 3b is satisfying. The moment I take lambda equal to 0, I solve for x and y, their sum comes out as less than 36. Hence, this is my answer. Okay, so with this, we are done with question number 1. I repeat, question number 1 is based on constrained optimization. And I have covered up constrained optimization in quite depth in my lectures within the advanced mathematical methods for economics course. So all students who are watching this particular lecture, you get the maximum benefits only when you subscribe to my complete course for advanced mathematical methods for economics offered at Delhi University in semester 3 of economics honors. I repeat, just doing the past year papers is not sufficient. In my lectures, you will see that I do a lot of practice. So make sure that to get the maximum benefits, you subscribe to my complete self-paced course for the advanced mathematical methods for economics course. I stop in this particular lecture. In the next lecture, I'm going to start with the discussion of question number 2. Okay, this is something I intend to look at in the next lecture. So I stop in this lecture. I hope students have enjoyed this lecture. Any doubts? You can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschooloфeconomics@gmail.com. This is where I stop in this lecture.